Okay. So in the last class, we just finished this slide, right? So in column, we have three stress formulas or three equations to figure out the critical load of the column or critical stress of the column. Number one formula is called Euler equation, and that Euler equation is used for long column. Another one is called Johnson column equation, that are used for short and intermediate column. And these two equations is used when a load is passing through the center of the cross section. In that case, we will use Euler equation for long column and Johnson equation for short column. Okay. And other equation is called second formula of column. That will be used when load is not going through the center of the cross section. So let me draw some cases. We have this kind of, say, rectangular cross section of column. If you apply load through the center of the cross section, then if this is a long column, we'll use Euler equation. And if this is a short column, we'll use Johnson equation. But if you apply load, for example, you are applying load at the corner. If you apply load at the corner, then how much the eccentricity? Eccentricity is this much. Okay, that means distance from here to here. This is the eccentricity because this load is not going through the center of the column. In that case, we'll use second formula. So one by one, all three equations we need to derive, and we need to explain you. That means we need to understand it. And other things, we are talking about long column and short column. How do you know a column is short or long? You are measuring with the tape and you say this is long, or even you have a short column and you can say, okay, this is look like short, so this is short column. Actually, that is not true. Because length of the column, it depends on cross section of the column and radius of gyration, and also depend on value of I. So there is some formula or scale or tool, I'll say some formula. If you use that formula, then you can say this column is long, this column is tall. Okay, so we'll derive those formula one by one, but right now we are deriving a formula that will be used for long column. So consider that formula is known as critical load of long slender column. Slender means slim, or derivation of Euler equation of long column. That means this column we can use only for long column. So considering a long slender bar, that means a column of length L, and cross-sectional area A. We are thinking this is a bar, cross-sectional area A, and this bar is carrying compressive load P, and bar is remain deflected shape between pin to pin support. This is pin support, this end is a pin support, and remain will be deflected shape. That means this is the P is the critical load of the column. So we need to determine that amount of load. Is it 500 pounds or it is 1000 pounds? That means we need a formula. Now, what are the assumptions you will make? Number one thing, we will think that cross section of the bar is constant throughout the length. That means bar length is not varying. Material of the bar is homogeneous and isotropic. That means material is homogeneous. If it is a alloy material, all the alloy mixing homogeneously and property is same in all directions. Material obey Hooke's law. This is the other assumption. And compressive load P acting through the centroid of the cross section. That assumption we are thinking. Okay. Now, how we can derive? Now you look that you have a beam, the horizontal beam. It has support at both ends, left end and right end. It's a simple support. And you apply load, then it is deformed, like it go like that. It is deformed like that. Now, if I ask you why it is deformed, what is the reason of it?
Because of load.
Because what's your name? ID?
Azmine 135.
135. Okay. Very good that you response it. I appreciate that. Okay. 135, right? I'm writing your right number. Okay. Good. You are saying because of load, but
Yes, sir.
it's true. But if I ask you, a non-technical person, he will say due to the load. But I am saying, yes, it will buckle due to the load. But why? What is the reason? The reason is that there is, what is the external load? Only say over here we apply 100 Newton load, right? That you can see from your eye. But these two load you cannot see. The reaction you cannot see. These are the internal load. Reaction and internal load you cannot see from outside. Okay, now in every section, every point of the beam is subject to a bending. Due to the application of load 100 Newton, there is a bending moment working in every point. And due to that bending moment, beam is bent. And the bending moment at the middle is maximum. So at the maximum, it bend more. Gradually, you move right side and left side, bending moment decrease, and beam bending more, bending is less, deflection is less. Okay. So you see, this beam is bending due to the bending moment working at all the point. Okay, could you hold down 1 second? Recording. So that's why it is bending in beam. That every point there is a bending moment working. Similarly, in the column, I show in the figure that is bending in upward direction, right? It might bend in downward direction. It depends. Anyway, it can bend. Why it is bending then? Because you are applying load at two ends parallel to the axis, but at each point there is a bending moment. That means bending moment. That's why it is bending. And for column, this bending you see, if I say this is x-axis along this direction, this is y-axis. So this deflection value of y is depends on x. That means x increase. If x become L by 2, a bending moment identified deflection more. X equal to L, deflection 0. That means y value 0. X equal to 0, deflection 0. But you need to remember everywhere there is a bending moment working. That's why it is bending, right? So
Yes,
you realize that there will be a bending. And from the beam, we know that actually what is this one? In the beam, something bending like that. So it's a you have simple support over here. You apply load, it is bending like that. But actually, this is become a arc. That means part of a circle.
circle.
So obviously it will have the radius, right?
Radius.
And
Yes,
this
sir.
radius will depend on what? Depends on how much bending you are applying. That means the curvature
Radius of curvature.
1 by rho is, you see, if radius decrease, then what will happen? This is a graph, right? Say this is a graph curve, and it has a radius rho. If radius decrease, then what will happen?
If rho decreases, then radius of curvature will increase.
Increase in other end, there will be more bend. That means it will gradually become a more curved circle. But if radius is increased, then gradually it become a
Decreasing.
straight line.
Straight line.
That means radius become infinite, then there will be no, if become infinite, then 1 by, what is the value of 1 by rho? 0. That means no curvature. Okay. So sometimes you go for job interview, sometimes people ask the question that what is the radius of a straight line? If you say there is no radius, that is not right answer. You have to say it radius is infinite. Okay. So that's why the bending moment and the radius and this bending moment and how much it will bend or radius, it depends on what type of material you will use. If you use stronger material, you need more bending. And if you use higher size material, bigger size material, it will less bending. That means this M rho will depend on value of modulus of elasticity and also the section property. That means moment of inertia. So it's saying relationship between bending moment, the radius of curvature
Radius of
rho
curvature.
is given by this formula. So this is equation 1. Other thing that what is the difference between a straight line and what is between the difference between graph?
So the radius of line is infinite.
Okay, let me, he can answer it. Then if he can do it, he'll answer. Okay. Sanjidul, roll 1 on 9. You are in front of the computer. Roll 1 on 9. Okay, he can. Rivan. Rivan 1 on 9. Okay, he can. Okay. 106.
Sir,
Who? 106, Majidul Haq. You are here? Majidul Haq? He is not here. He left. Okay. Someone was trying to answer. Tell me.
Sir, for the straight line, the radius is infinite.
Infinite.
And
then
for straight line.
for straight line, other than it has a radius, right?
Yes, sir.
That's one characteristics or one point. What is the all other point? In terms of slope, what is the straight line? Its slope is constant, either 0 or either it has a certain value of the slope.
Certain value of slope. Yes.
That means dy by dx, value of dy by dx will be constant all the way, right?
Yes, sir.
In the graph, curve, is his value
It
of
will
dy
vary.
by dx will change. That means every point, if dy by dx value is not constant.
Same.
Okay. So, and also you see this slope of a variation of slope of a curve depends on also radius of curvature. So that means there is a relationship between slope and radius of curvature. So that's why from the mathematics we use this equation. That equation of curvature 1 by rho equal to d square y by dx square by and also bottom equation. Now
Sir, we got a smaller equation yesterday, last class.
Okay, tell me, yeah.
Sir, d square x by dy square for the radius of curvature.
Right. Ultimately, it will come the 1 by rho equal to d square y by dx square. I am just repeating again. But I'm saying if I expand the bottom series, then there the first term will be 1, next term will be dy by dx whole cube. Okay. So dy by dx, the slope will be minimum, or you can say what is the dy? Dy means distance between 2 point dy, and dx is a distance between x distance between 2 points. So if I say this is a small value, for simplification, we can say 1 by rho equal to only this value. Okay. So let's see in the next slide. Okay, what was your ID? You answer some question.
Sir, 135.
135. Okay, I will cross check, sometime ask questions. So I like to know the whether you are in the front of the computer or you are just hook up in the class and playing PUBG, okay, in cell phone. So I need to make sure. Okay, now, so that's why we are getting this equation, that 1 by rho equal to this one. Now this 1 by rho, if I substitute right over here, 1 by rho equal to this value, input over here, then you will get this equation, a differential equation, M. Now you see, now in the column, if you apply load only the 2m, right? Now you obviously you have question in the mind that how we figure out the m. So what we did, we cut the beam with a knife, not beam, sorry, the column at any point we can cut. I cut it right over here at the point A, and I try to look how many force could work at point A. So if you make a free body, other thing we are working with the static body, not the dynamic body. That body is static, is not moving. So you see at the left point we have force P working toward right, and this side force also should be, reaction force should be P, right? Opposite and same. Then summation of force along x direction is 0, right? But you
Yes,
look
sir.
to the free body, is it balanced or no?
No, sir.
What happening? It
Yes,
is
sir.
what happened?
Not balanced,
Why
sir.
not balance?
Because, sir, yeah, there is shear force and bending moment, sir.
No shear force, but bending moment. What is your ID?
Sir, 106.
106. Okay, good. You answer 2 questions. There is a bending moment. Shear force work parallel to the cross section. Okay, so there is no shear force. This force P working perpendicular to the cross section. Now we see this P working along this direction, this P working along this direction. That means, and there is a distance between these two points, right? 2 points. That means it is rotating. It is rotating along opposite of clockwise direction, anti-clockwise direction. This is pushing along this direction, and this P pushing along this direction. That means this body is rotating. So you need to put some rotation, I mean moment. So how we can protect? You see, this is rotating anti-clockwise. So you stop it by clockwise moment. I'm saying this is M. Now, how I can figure out the value of M? You take moment over here. So if vertical distance, this point is Y, then what will be value of M? Then M will be P into Y, right? P into Y. You take moment over here, moment for this force will be 0, M working clockwise. So you say, if you say clockwise positive, then plus M, and this P try to rotate anti-clockwise. So moment will be P into Y, and this is minus. So equal to Py. That means M equal to Py equal to 0. Then you get value of M. Now you see this value of M will depend where you are cutting. You are cutting right over here, there will be one value. You cutting here, there is one value. That means it is M is function of X. So that's why you look in this free body. I put M of X right over here. This is M of X. But over here coming clockwise, right? But I put anti-clockwise just for convenience to solve the differential equation. But this is nothing wrong because you will get just negative value instead of positive value. Okay. So this is my free body. So I'll get mx equal to minus p into this y. And that m we will put in that differential equation. So let's see. Over here, we got this equation m by ei. Now we know that this m vary with x. So that's why instead of putting m, only m, just we put mx. So d square y by dx square equal to mx divided by ei. Okay. Now see, this is a differential equation, second order differential equation. So if we solve this differential equation, you get value of y equal to something. Then you can figure out the load, because you see mx equal to what will happen? Value of mx equal to, you will get minus p into y. So ultimately this equation is coming in relative with relation of p, not the m. So let's see what in the next slide what we'll do. We'll put value of mx equal to minus py right over here. Okay, then we solve the differential equation. So you look at over here that d square y equal to minus py by ei. Then just rearrange this equation. Okay, p by ei. Then for our simplification, to solve the differential equation, we are thinking that this value equal to k square, a constant. This will be obvious constant because load you are applying, you are not varying. E modulus of elasticity, that is constant. I is the moment of inertia, also constant, right? So this value will be a constant. So right over here, then it becoming d square y dx square plus k square y equal to 0. So this is our main differential equation. So this is a second order differential equation. So if you solve it, then there will be two constants. Okay, C1, C2. So you learn mathematics in second year and first year, and you might don't know that why we are studying mathematics. So here is the application. But this is not the math class, right? So what we are doing, we just taking the solution, not the solve the total differential equation. So solution will come yx equal to c1 into sine kx plus c2 into cos kx. But instead of c1, c2, we just put two constant c and d. Now you see there is a two constant. So to solve these two constant, what do you need? How many boundary conditions you need? Anyone who can tell me? We have second order differential equation.
At least two, sir.
Good. At least two. Your ID?
106, sir.
Your ID 106. Okay. Your name?
Sir, Majidul Haq.
Majidul Haq. Okay. Good. So we need two boundary conditions. And if you look in the figure, we can figure out two boundary conditions, because when x equal to 0, what will be value of y? 0, right? Because x equal to 0, that means you are right this point. Right this point, y value 0. And if you put x equal to L, then what will be value of y? 0. So these two boundary conditions will apply equation 5 we'll get value up to constant. Okay. Now you see this is the boundary condition. X0, x equal to 0, y0 equal to 0. That means y0 mean y value at x equal to 0. How? Similarly, x equal to L. So y value at x equal to L equal to 0. And now we'll apply over here. You see, if you apply first equation, then what will you get? X0, y0, that means 0. This will be 0. This will be sine 0. Sine 0 mean 0, right? Then cos 0 equal to 1. Then you are getting what you are getting actually. D equal to 0 you are getting. So let's see in the next slide. We are getting right over here. D equal to 0. Now we will put the second boundary condition. What is our second boundary condition? X equal to L, y L equal to 0. So our equation is yx, this one. So our main equation is this equation. Over here we will put x equal to L. So you get yl. C sine kl. D cos kl. But we already found D equal to 0. So this will be 0. So now you are getting C sine kl equal to 0. Now tell me, which value is 0? C or sine kl?
C, sir.
C. Okay. If C value is 0, then what will happen? Already we got D 0, right? Then C 0, then what will happen? Y value 0. That means no deflection.
The C cannot be 0.
So value of C cannot be 0.
0.
If value of C cannot be 0, then sine KL should be
0.
So that's why we are saying the value of C cannot be 0. So sine KL equal to 0. And at the KL, we put the KL equal to this value, we put it over here. Now, you have 0 over here. So this 0 means you can put sine 0, right? So if you put sine 0, then mean a value becoming 0. So if sine 0 over here, then again, you see yx is coming equal to 0. Because value of sine 0 equal to 0. So if you put sine KL equal to 0 equal to sine 0, though this is accurate, but we cannot apply in this equation. So we will think that this KL, sine KL equal to sine n pi. That means n value can be vary from 1, not from 0. That we can say n equal to 1, then angle will be how much? 180 degree. N equal to 2, 360 degree. So gradually increment 180 degree. Now, if we take out sine from the both side and then square root, we can figure out the value of p. So let's see. So right over here, we got take out the sine. We got this one. We make the whole square. Then we got the p equal to n square pi square l square. This is our formula. So what is the P? P is the load applied in the column. And for critical load, we need to figure out what is the minimum load it can carry in the deflected shape. So how P vary? You look in the over here, the length of the column constant. Pi is a constant. E material constant, right? And I can be varied because if you can use a bigger size cross section, you can use smaller size cross section. Other thing, value of I, actually a cross section will have two I, IXX and IY. Sometimes IXX and IY cannot be same. So value of P will be minimum or smallest, right? So for which value? If I is minimum, then I put I minimum. And if n equal to 1, then P will be minimum, right? So in that case, instead of calling it only P, we will call it P critical. So P critical equal to pi square E I minimum by L square. And you see, we know radius of gyration equal to this mass. And if you square root, you get the I minimum equal to this one. This I minimum you can put in right over here. So if you put right there, then just rearranging the equation will get some other value. Let's see what we found. Right over here. So this is finally, if you just simplify, then you get this equation. This equation. Now this equation again, I can simplify more. How? This rho square, I can put bottom of the L. L by rho square. Pi square E A L by rho square. And this A, I can put bottom of P critical. So P critical by A equal to pi square E L by rho whole square. Now P critical by R, what does it mean? Stress, P by 4 stress. But instead of stress, we can call it critical stress. So critical stress equal to pi square E L by rho whole square. And what is the L by rho? It is called slenderness ratio. And this equation is known as Euler equation of column. And sigma critical is known as critical stress of column. Above formula is derived for pin-to-pin support. And for other support, now you see when you derive, then what do you assume? That column has pin support at the both end. Now, if you have a column that one end like that, one end fixed like electrical pole, top end free, and you have compressive load. You can apply Euler equation directly over here. Anyone?
Sir, can you repeat?
I am asking question roll 157. Ornov. Ornov, you hear? No. Nabil, roll 155. You're not here. Momi. Momi, 154. Hasnath, 150.
Yes, sir.
150, you are here?
Yes, sir.
Okay. So tell me, we derived this equation for pin-to-pin support, both end pin. Now we have electrical pole. Ground is fixed in the bottom. And at the top is free, right? Then we apply load. In that case, we can apply Euler equation.
Yes, sir, we can.
How we derive, which end condition we derive? We derive for pin-to-pin support, right?
Yes, sir.
Both end is pin. But right now, what do you see over here? Only one end free. The top end is free because it can move along this direction, it can move along this direction. And bottom is fixed. That means one end fixed, other end free. So this is not the, you cannot use the Euler equation right over here. Okay? Because end condition is not the same. So what we did to make the Euler equation is a general equation that you can apply this equation in every column. That's why we add a end condition of the column, a constant. This is C. That means Euler equation is become P critical by A or sigma critical pi square EC divided by L by rho whole square. And EC is the end condition of the column. Clear now?
Sir, end condition বলতে কি বোঝাচ্ছে স্যার?
End condition mean, I will explain it later on. End condition mean, for example, I think other day I told you already, say you are taking a bag on your head. You get down from the bus stop, there is no rainy and icy, nothing is there. And also you lost your shoes. So you're walking with barefoot. What will happen? There is a more possibility that you will get sleep, right? Due to the load. But if you have a shoe, or boot in your feet, even you can take 3 bags on your head. Why? There will be no slip between your feet and the ground. That means, so load on a column, it depends on the end condition. If end condition is like very strong, then column will carry more load. You understand? But
Yes, sir.
Euler equation we derive for pin-to-pin condition. But what does it mean pin-to-pin condition? Anyone? Let me I explain you. You see my pen, right? So if I hold it with between 2 fingers, what does it mean? I hold it tightly. That means I am not allowing to move this pen upward direction. It will not move in horizontal direction. That means XY direction, it cannot move because I hold it with the pin support. But it can rotate. That means it is not, rotational constant is not there. That means this end support, pin support, cannot say, hey guy, you cannot rotate. Because he is weak. He only say, you cannot move in Y direction, you cannot move in X direction. But if I hold it like that, with like my finger like that, then I cannot turn it because it has some rotational constant. This is a fixed support. So if both end is fixed, then that column you can apply more compressive load. If like that one end on the bottom is fixed, upper is free, then it will carry less load. If you apply load, immediately it will like bend like that, this way or this way or this way. So column in the load depends on end condition C. So that's why we put a constant C. So if we figure out the end condition for all the column, then we can use this Euler equation for all the column, all the end condition. That's how you put a C. Now tell me, what will be the value of C for a pin-to-pin column? Value of
One.
C, how to say?
Sir, 1,
1, good. You ready?
131.
131. Okay. This will be 1. Then, because if you put 1, then we are going back to Euler equation, right? We are going back to over here. So let's see. I will explain it in detail that what does it mean the end condition of column. So let's see. Right over here, we just simplify or rearrange the column equation. How? Euler equation. You see, we know we have this equation. So right over here, this is my mistake. This will be L. This will be L. So L by pi square is C L by K square. Now, this C, we put it bottom, like 1 by C. Then I take out 1 by K whole square. And this is not 1 by K, this is L by K whole square. Okay. And this C, I write down 1 by root over C whole square. Then I rearrange like that. L by root over C whole square, this is K square. Now, L by root over C, this term, I can say this is the effective length of column. And I will explain it. What is the effective length of column? So right now, you just remember, effective length of column LE equal to L by root over C. Now we see, instead of this term, right over here, I can put LE. LE square by K square. So after simplification, we are getting this equation. I square E divided by LE by K square. If you don't like this format, you can use this format. The result will be same. Now, you see there is a E right over here. What is the E? Modulus of elasticity. And you study stress strain graph, right? So in the stress strain graph, you got value of E for what type of test? Tensile or compressive? Did you remember?
Probably tensile.
Compressive.
Tensile. We teach you in the first chapter by Shahana Sir, that was for tensile test, it was go like that. Okay. So this E will be modulus of elasticity for tensile. But if we apply by compressive load, then modulus of elasticity for compressive compression will be EC. But in general, if material is ductile, then ET and EC are same. So that's why a lot of book it say EC equal to ET equal to E. But in column, you say we are applying compressive load, right? So it is better, instead of using ET, you use EC. For ductile material, EC, ET is same, but in proportional life, for example, if we use aluminum in the aircraft or in a helicopter or design a missile or space shuttle, then lot of type is aluminum, and some aluminum has a different value. Though aluminum is ductile, still you will see value of ET and value of EC is not the same. So you look in the material property in the handbook, you will see there are two values given, ET and EC. Now for column, which one you use? If you use ET, that will be wrong, because column taking compressive load. So you have to take
Compressive
only
load only.
EC.
EC.
Okay. So you need to remember this one. So this is our Euler equation of column. Now you need to know that what is actually equivalent length. What does it mean? It's coming from the one problem that we derive Euler equation for pin-to-pin support. We're not deriving for other support, like both end fixed, one end free, and other end is pin. No, we derive only for one end condition. So that's why we need to figure out the end condition for other column. For example, if you look this first figure, figure A, then you see this is a pin end, bottom pin end. So that means this is exactly matched with our formula, right?
Yes, sir.
We derive the Euler equation. So what will the value of C for this column? Immediately you can say value of C equal to 1. And the length of this column is 2.5. This one also 2.5. All of them length is 2.5. But this column you see, this end is fixed, this end is fixed. What does it mean? That it will behave like a shorter column. Column length shorter, that means it carry more load. Column go bigger, it will carry less load, because you made bigger, you apply load, it will buckle, right? So this figure B, all of them have length 2.5. But if you think that this is a pin-to-pin column, then its length will be half, 1.25. That means, say you have two columns, both end fixed, length is this much. That means length is from here to here. And you have another column, length is this much, and both end is pin. So in that case, this column and the bigger column will carry same load. That means this column equivalent to pin-to-pin support of this column. This is length is shorter. So that's why it become how much? The half of 2.5. So value of C will be 4. So L by root over 4, that means L by 2. Similarly, if you have one end fixed and one end free column, then this length is L, right? But it will behave like a long column. That means long pin-to-pin column. A pin-to-pin column, if its length is this much, that means its length become, this is pin-to-pin, this is pin-to-pin. So if this length is 2.5, but and this I draw the red line, this length is 5 meters. Both will carry same meter. That means a one end free, one end pin column, you are converting into pin-to-pin column by using the end condition formula. Okay. Similarly, this end is pin, this end is fixed, and you will get load only this much, equivalent length. That means value of C become 2. So for the exam, for design, you need to remember this n condition. If both n fixed, C equal to 4. Both n pin, C equal to 1. 1 n free, 1 n fixed, 1 by 4. 1 n pin, 1 n fixed, C equal to 2. Okay?
Sir,
Yes.
it's not clear why the equivalent pin-to-pin length is differing.
What's the difference?
Yes.
That means we derive the Euler equation for pin to pin, right? But
Yes, sir.
look in the figure B. This is not pin to pin, right?
Yes,
So
sir.
you cannot use the this Euler equation right over here. But this column will behave like a pin to pin column of half length, half of its length. That means this much length. So if length is L, what will be half length? L by 2, right?
Yes, sir. But how it is calculated that?
So how
on
it is
half length?
calculated? Okay, good. It is calculated based on experimental data. You got it?
Sir, can you tell me again?
By experiment.
Okay,
Say
sir.
you are taking two columns. A column with length 1.25, this column. And you take a other column, length is 2.5 with both end fixed. And this one, but this length is double of this one, right?
Yes,
Due
sir.
to the experiment, you will see both on carrying same load. Now,
Okay, sir.
you got your answer?
Yes, sir.
So if you got this kind of column, then you obviously think its equivalent length. That means conversion length will be half of this length. Thus you put L equal to L by root over C, and you put C equal to 4.
Sir,
Yes.
that means we'll need to take this lens to carry same load, the same
We-
load for different conditions, for different end conditions.
Yeah. You see, if you look in the figure B, you take a column, length is 2.5, say 2.5 feet, and you apply the load. N condition, both N is fixed. You can try in solid mechanics lab. Say it carry, you see, buckle, compressive load carry 500 Newton. Okay. Then you take a half of size of this one. Take a pin to pin support column. You will see that one also carry 500.
Okay, sir. Got it.
Okay. Now clear?
Thank you. Yes, sir.
Okay. So let's see what we have. Okay. I like to give you how long our class until
Sir, we have more 45 minutes.
more 45 minutes, right?
Sir.
Let's see how much time we have. Right now is 12:38, right? What time we start? No, 1:55 right now, right? And our
Yes, sir.
class,
Yes, sir.
how long will continue our class?
240.
Sir.
2:40. Okay. So what I can do, I can give you 5-minute break. Okay.
Okay, sir.
Okay,
Come
sir.
back 2 o'clock, then we will start the second one. Okay. So I am
Okay, sir.
putting everything on stop the. Okay. So we can start from here. So, you see here, we derive Euler equation for long column, right? So
Yes, sir.
how did you know a column is a short or long? Euler, he don't give that formula. I only you look to the cross section and length of the column. You cannot determine it is a long column, it is a short column. Sometimes a very short column, even only 1 feet length, it behave like a long column. Like you have, example, if you have a steel scale, 12-inch scale, you just press it, it will deflect, right? So even if it is a short column, but its behavior is like a long column. Similarly, if you have a very long column and strong cross section, you cannot buckle. That means it behaves like a short column. So to figure out the behavior of short and long column, are we able to hear?
Yes, sir.
Hello?
Yes, sir.
Because it's raining extremely heavily, So if you are not able to hear, you can just send me message, chat box, or you can tell me loudly, sir, we are not able to listen. Okay.
Okay, sir.
So Johnson, what he did, he take number of columns, say 100 columns, and he take them in the lab, and he vary the length of the column. So if vary length of the column, that means he vary the slenderness ratio of the column. That means L by rho or L by K. This ratio is called slenderness ratio. Some will write down L by K, some will go with L by rho. Both are the same thing. And this is our Euler equation. Euler equation right over here, we have L by K. So what Johnson did, he take number of columns in the lab, solid mechanics lab, and he cut in different length, but cross section is same. When cross section is same, then L by rho ratio will vary, right? Then he tried to make it graph. How he make a graph? Along horizontal axis, he put L by K or L by rho. And about vertical axis, he put sigma critical. Sigma critical means P critical by A. Then he figure out that how column fail. Say he pick up one column, his L by rho is right over here. And he test it, then he's saying, when stress is this much, it is fail. And he took the other column, say L by rho right over here. And he's fail with this much stress. And that means this much is the stress. Similarly, he got number of columns. And he got number of points in several locations. Right? And he found that if L by rho is low, then some of the column failing like that. They're right over here, coming like that. And he observed that some column is following this path. What is the Johnson Euler equation? If I say P by critical equal to Y, I'm saying this is Y. Equal to, along Y axis we put P by critical. So this is Y. And if C constant, pi square constant, E constant, that means if I say C1 divided by L by K square. L by K square means this is X square. So this is parabolic. So he found that some of the column exactly maintain the Euler path. So that means this P, Q, T, R is the Euler path. Then he found that if L by rho is become low, then some column coming like that, all the points. And you see line BT also parabolic. He figure out. But he don't know the equation. So you need to figure out this equation of line BT. We already know Euler equation formula. But equation for line BT, we don't know. So we need to figure out. So how we can figure out this line? So let's see. And right over here you see that point T is a common point. It is on this graph. Also, this is on this graph. Okay. Are you able to listen?
Yes, sir.
Yes, sir.
Okay. So if T is the common point, what is L by rho? If you make a line, cut it over here. Then he identified this one as a L by K1. And he figured out that stress at point A become 0.5 SY. 0.5 SY means some book write down S as a stress. That means yield strength. Some book write down sigma Y as a yield strength. Some book write down Fy as a yield strength. So he found that column failing at point T at half of yield strength. So this is one condition, that if L by rho is this mass, then this column fails at 0.5 of yield strength. And this point T lying on Euler curve and what is lying on parabolic curve. So other thing he observed that a column, how much maximum stress it can allow. Stress cannot be more than yield strength. Because if yield strength is more than stress is more than yield strength, then what will happen? There will be plastic deformation. There will be material will fail. So he is saying maximum load can take by a column will be equal to yield strength. That means only equal to this much at point B. So if you look at point B, what happened point B? What is the L by rho? 0. So if L by K or L by rho equal to 0, then column taking on the load sigma Y. So you see from this graph we are getting two conditions. For point B, L by K or L by rho, whatever you say, equal to 0. And sigma critical becoming sigma Y. And for point P, L by rho become how much? L by K1. What is the stress? 0.5 sigma Y. So these two conditions we have. Based on these two conditions, he figure out a equation with some constant. So let's see what he figure out. He figure out this equation. He's saying the line BT, equation of line BT will be this one. Now, there is a two constant, A and B. If you figure out these two constants, then you can found that equation. And you see you have two boundary conditions. You look, L by K 0, stress equal to how much? Sigma Y. So A equal to sigma Y, you already get it. Right over here by applying this condition. And we'll apply second condition, this one, that L by K equal to L by K1 and stress is this mass. So let's see. Right over here, we found SOI equal to this mass. Now, we need to figure out the constant B. This value we found. We need to figure out this one, B. But you remember one thing. Point B in the same two curve, the common point. So this condition I can apply in Euler equation. So if I put Euler equation, if I put condition B, what is the condition B? L by K equal to L by K1 or L by critical. What is your stress? This is sigma equal to 0.5 SY. This coordinate you put over here, right over here. So we put sigma critical equal to 0.5 SY. Pi square EC. Instead of L by K1, we are putting L by K1 critical. Why critical? I'll tell you later. Now this L by K critical is coming this one. Okay. Why L by K critical? If you staying on right side of L by K1, column behavior like Euler equation. But if you are left side of this L by K1, column behavior like a short column. So that's why they say that this is critical slenderness ratio. And if you look carefully, this ratio, and there is no length of the column, only end condition, E, and material property. Okay, so we got one formula. Now we'll apply this one. How we got this one? By applying right over here. Now same coordinate will apply in 0.5 s. Okay, so let's see how we can apply here. Oh, it's rain heavily. Okay, right over here, value of A we already know. Value of constant A equal to SY, we know. And how was the stress? 0.5 SY. 0.5 SY. This P critical A equal to 0.5 SY. Then L by K1 square. Actually, L by K1 and L by K critical is the same. That we already figured out right over here. Now, this value you put over here. Then you just simplify the equation, you get value of B. So now we see we get value of B, we got value of A. These two value, you put it right over here, and you will get the equation. So let's see. So after you put the value of A and B, this is B, this is A. You put it over here, then you get this equation. And you simplify a little bit. Finally, you are getting this. And remember, this one is L by K. Okay, so this equation is known as Johnson equation for short column. And if L by K is less than this value, column will work like a short column. If your L by K is greater than L by K critical, then it will behave like a long column. That means your right side, you need to use Euler equation. Your left side or your right over here, you need to use Johnson equation. So, any question?
স্যার কার্ভটা আর একটু বুঝিয়ে দিলে ভালো হয় স্যার।
Hello, are you hear me?
Yes, sir.
Okay, I think we can stop it because extended raining over here. So in the next class, we'll discuss all those things. Okay.
Okay, sir.
Okay, sir.